we're going to look at the second law of thermodynamics in terms of entropy. The entropy is the degree of disorder. What entropy is about is the number of ways that things can happen. So the more ways you have, the more disorder and the more likely it is to happen. If you were to throw two coins, you could possibly get a head and a head and a tail and a head, or two tails. So there's one way of getting two heads, there is one way of getting two tails, but there are two ways of getting one head and one tail. So since a head-tail combination is more likely, there are more ways for it to happen. This means it has a greater entropy. There's more ways for it to happen, greater level of disorder. Now, here we have a chessboard, and we have one particle. Now, how many ways can we arrange that particle on this chessboard? Well, there are basically 64 possibilities. Now, if I put more particles, there's going to be more ways. Put two, that, and that. How many ways can I organize 4 there? It's much more chaotic. There are many more ways, but it's much more likely to be scattered around than it is all going to be in the one square which we had in the first place. The first square was a high level of order. Like this is a high level of disorder, which means more entropy. You need to state that the entropy is a system property that expresses the degree of disorder in the system. Now let's say that we take all these gas molecules in these two boxes here at normal temperatures and inside closed containers. Now the one on the top right, we know that's highly ordered, and that can only basically happen in one way. If you look at one on the left, it's highly disordered, they're scattered all over the place, it's much more chaotic, you have a much higher level of entropy. Now, it's not possible really for the scattered particles to go back to the original that we had in the first place. So sometimes entropy is looked at as the times arrow, let's say. Things tend to be more chaotic. A second example, if you threw a lot of bricks off a truck, what kind of pile are you most likely to produce? The one on the left, which is completely ordered and organized, or the one on the right, which is chaotic? Well, the disorder is much more likely to happen, which means a high level of entropy. So on the right, we have a high degree of order, left, high degree of disorder. Now, this law is a law of physics. Everything tends to be the greatest level of disorder. In the universe, the entropy is always increasing. It always becomes more disordered, and it will never decrease. An example of entropy is that heat goes from hot to cold. Heat spreads out, and it means that the entropy increases. There are many more ways for heat to be spread out in a system than they are to be compacted in a small place. If we take this example on the top right again, the top right is all the heat is concentrated in the top left hand corner. It's not likely to stay there, it's likely to spread out. Heat spreads out. That increases the possibilities, the combinations, and that will increase the level of disorder. Now, if entropy decreases in one place, and that can happen, it means it must increase somewhere else. There must be some mechanism that is making it decrease, but in engaging that mechanism, it means that there will be an increase of entropy elsewhere, which must compensate for it. So in other words, the law of entropy is a statistical law. Things happen where you get disorder because there are more ways for it to happen. And the more ways that there are for something to happen, the more likely it will happen. So we need to look at this entropy formula 1. This is it. We need to define these terms. Delta S is the change of entropy. Delta Q is a transfer of thermal energy. T is the temperature of the body. So what are the units of entropy? It's delta Q, which is joules, divided by temperature, which is K. So it's going to be joules per Kelvin. You should note that this works for small changes of temperature only. If it's not for small changes, then if the temperature changes, then we have to do an integral, but you won't be expected to do that. So let's look at an example here. We've got two bodies next to each other. One is hot, which is at 400 Kelvin. One is cold, which is 200 Kelvin. So the one on the left has many units of energy. There's a large disorder and there's a large value for entropy. The one on the right has fewer units of energy. It's quite ordered, and so there's a small entropy. Now, the formula for the entropy change is delta S is equal to delta Q divided by T. And we're going to end up in this situation where we end up with this thermal equilibrium. They're both at 300 Kelvin. So, what is the energy transfer? You're told that it's 4,000 joules. So we do the calculation. The entropy change is delta S is equal to 4,000, which is the energy, divided by the temperature, which is 400, gives an entropy decrease of 10 joules per Kelvin. So in losing some of its thermal energy, its entropy decreases. Now the rule is that if one body has reduced entropy, this must be compensated by the entropy in somewhere else. Now do the calculation for the entropy change in the right box. The entropy change is 4,000, it's the same energy flow, divided by 200, which is plus 20 joules per Kelvin. So in other words, the entropy change of the hot is minus 10. The entropy change for the blue one, the cold one, is plus 20. So the hot object loses 10 units of entropy. The cool gains 20 units of entropy. Therefore, in the universe, the entropy increases. So this is an example of why heat goes from hot to cold, because it must to increase the level of entropy.